I am Anil Kumar. Welcome to my YouTube channel and the website Global Math Institute. In this video, we'll discuss reciprocal and rational functions. Focus will be on key features and how do we sketch graph of these functions. In case you want to join my classes, you can always send an email on the address given. Let us now enjoy the journey of success with Krishna. Hi Krishna, how are you doing?
Hi, I'm doing good. How are you, sir?
Very good, very good. So, how have been your tests so far?
Oh, they've been great so far. I've got high 90s so
High
far.
9 is pretty good. So, for the benefit of our viewers, will you introduce yourself, please?
All right. Hi, I'm Krishna, and I'm in grade 12.
Perfect. So, Krishna, which is the chapter which you would like to understand today?
In school right now, we're working on chapter 5,
Right.
which is reciprocal functions and rational functions.
Great. So, do you understand these two?
Yeah, I understand these two
Understand.
topics.
So, let us check a bit about it and then we'll begin our class with what you really need to understand. Is it okay?
Yeah, that's okay.
So, can you tell me what are rational functions?
A rational function is a polynomial divided by another polynomial.
We could say quotient of two
Yeah,
polynomials. That's
correct.
correct. What else could you add to this definition?
Uh, they would have vertical asymptotes since the denominator can be 0.
What? When we say rational functions is a quotient of two polynomials, and of course, the denominator cannot be 0. But denominator being 0 could lead to either a whole or a vertical asymptote. You get the idea? Not always
Yeah,
a vertical asymptote.
yeah,
And there could be situations where there may not be any asymptote.
yeah, correct.
Realize that.
Yeah,
Okay, so let's begin by saying a general example. What could be a situation where we will not have any vertical asymptote or even a whole for a rational function? Can you give me one example?
it could be that um the denominator is just a whole number.
Okay, that's a good answer. Denominator could be a whole number, and that gives you a very good point, and that is even the whole numbers are considered to be polynomials. Right? Some
Yeah,
students think that whole numbers and straight line y equals to mx plus b does not belong to this category of polynomials, since while defining polynomials, sometimes we say poly means many, right? So we have
yeah,
many terms,
correct.
right? Okay. And we always have a variable in it, right? That's it. But we should know that polynomials are closed when we do addition or subtraction or even multiplication. They are not closed for division, and that's why we have rational functions.
Yeah,
Closed
okay.
really means that if we add polynomials or subtract polynomials, we will get a polynomial, right?
Yeah,
So you could get a
correct.
number after adding or subtracting a polynomial, and therefore that is also a polynomial. This is another way of looking into it. Is that clear to you?
Yeah, that's clear.
Very good. Now I'll give you another example where we will not have any vertical asymptote or even a whole, and that is ensure that the denominator is always positive. For example, x squared plus 1, right?
Yeah,
If
correct.
I put x squared plus 1 in the denominator, then x squared plus 1 does not have any real zero. Therefore, there won't be any vertical asymptote. Getting the point,
Yeah,
right?
yeah, that's correct.
Perfect. Now, when do you have a whole?
It's when there's two common factors in the top and the bottom.
Correct. And they cancel out.
Yeah,
So basically, when you are simplifying your rational functions, all the common factors which cancel out from numerator and denominator will definitely lead to a whole. Perfect.
yeah, correct.
And those which remain will lead to vertical asymptote, and that is how we will identify which factor will lead to vertical asymptote and which factor will result into a whole. Perfect.
Yeah, perfect.
Now let's talk about horizontal asymptotes, right? We
Okay.
just looked into discontinuities, and the two discontinuities which we found will be there or can be there in a rational function are vertical asymptotes and wholes.
Yep.
Now we are looking into what happens when x value is very, very large. It could be positive infinity or negative infinity. So when x approaches a large value, positive or negative, if y approaches a real number, then we say that the horizontal asymptote exists.
Yep. Okay.
Now, can you tell me if we have a reciprocal function, 1 over f of x,
Yeah.
then what is going to be the horizontal asymptote?
Uh, it would be 0. The horizontal
Y
asymptote.
equals to 0.
Yeah, y equals to 0.
Because, see, when the denominator function, it is going to approach large value as x approaches infinitely large value. So you're dividing numerator, which is normally a constant or just 1, by a very large number. So when you do that, you will approach 0. You're approaching a value 0, and therefore the horizontal asymptote equation will be y equals to 0, a horizontal line. Is that clear to you?
Yeah, that's clear.
Good. Now let's talk about the rational functions. In rational functions, there could be a polynomial on the top, polynomial in the denominator. When do we get a horizontal asymptote?
If the degree is the same, it's the leading coefficient of the top divided by the leading coefficient of the bottom.
Okay, so that is one case, definitely.
Yep.
And if the degree of denominator is higher, then
If the denominator is higher, then it would just be 0. Then y
y
equals
equals
0.
to 0. Perfect.
Yeah.
So we get horizontal asymptotes in case of rational functions whenever the degree of denominator is higher or degree of numerator and denominators are exactly same. For example, degree 2, right?
Yeah.
But
Correct.
you did answer the question. That is, the horizontal asymptote will be y equals to the ratio of leading coefficients in numerator and denominator, right?
Yeah. Right.
You know how do we achieve at this result?
Uh, no, I don't know.
So let's look into that case.
Okay.
Okay. So I'll share with you a screen now, and then we'll quickly go through the case. Few examples. So let me rewrite. So we are talking about rational functions. Let's say r of x is my rational function, which has some numerator and some denominator d of x. And clearly, the restriction is because d of x can be 0. So we write d of x is not equal to 0. Perfect. Now we
Okay.
are taking horizontal asymptote case, right? And we are taking a special case when degree of numerator and denominator is exactly same. Clear?
Yeah, that's clear.
And you are actually very comfortable with the subject. You know a lot. You're a top grade student, and you know the answer for this also. And it is the ratio of leading coefficients. But now we are going to algebraically understand why it is so. Perfect?
Okay.
Let me take an example. Let us say the rational function given to us is something like 2x squared minus, let's say, x plus 3. And we'll write some denominator like 3x squared plus 5x plus 1. So clearly, the degree of numerator and denominator is
They're
same,
the same. Yeah.
2, degree 2. Now, what you could do here is you could factor out x squared from both numerator and denominator. As soon as you factor out x squared, you get 2 here, right? Divided by x squared minus x divided by x squared is 1 over x.
Yeah. Correct.
And then 3 divided by x squared will be 3 over x squared. And in the denominator, what do we get? We factor out x squared, we get 3 plus 5 over x, and then plus 1 over x squared. We have taken x squared common.
Yeah.
Well, anybody can open using distributive property and check that these are the same results, correct?
Yeah. Correct.
Now, what we can do is x squared can be cancelled from numerator and denominator.
Right.
Perfect. Now, if you look into the case that x is approaching positive or negative infinity, that is a very large value. In that case, what will happen to 1 over x? It will approach 0, right?
Right.
And definitely 1 over x squared will also approach 0. So that clearly indicates that these two parameters which we have, they will approach 0 in the numerator, and this will also approach 0, correct?
Yeah, correct.
And therefore, if we take the case when x approaches positive infinity or when x approaches negative infinity, then these cases exist, right?
Yeah,
And therefore, I could write my rational function as equal to what? 2 over 3. Do you see that? Because all other things are 0 in this particular thing, right?
yeah, correct.
So our rational function is not equal to, I should say, is approaching, correct?
Okay.
So since it is approaching, we have a horizontal asymptote, which is y equals to 2 over 3. And clearly, you can see that this value of y is the ratio of leading coefficient. Is that clear to you?
Yeah, that's clear.
That is how you do it. Perfect.
Perfect.
So now we understand that if both numerator and denominator degrees are same, we do get a horizontal asymptote. And the value is y equals to ratio of these two leading coefficients. Okay, so now let's talk about any other kind of asymptote. Do you find any other kind of asymptote in rational functions?
You can find an oblique asymptote.
Perfect. And when do you get an oblique asymptote?
It's when the top is bigger than the bottom by 1 degree.
Very good. So let me clear the screen and take up that case. So let us say we have a rational function, okay, and this time we are keeping degree of the numerator slightly higher. Let's say 2x cubed plus 3x squared minus x plus 5. I'm just writing random values here. And then in the denominator, we have x squared plus x minus 1. So degree of numerator is 1 higher. So what is going to be the oblique asymptote?
Um, would it be uh no, I'm not exactly sure.
So we should divide the numerator by denominator. If we divide, what happens? Let's just check it out. I just wrote it right. So we'll do long division, simple. You could do synthetic division also. 3x squared minus x plus 5 dividing by x squared plus x minus 1. So first time you will go by 2, right?
Yeah, correct.
2x cubed plus 2x squared minus 2x take away. So we get x squared here, and this take away will give me plus x plus bring down 5, and then it can go one time, correct? We
Yeah,
get x
correct.
squared plus x minus 1, and when you take away, you get remainder 6. Perfect.
Yeah,
So
perfect.
basically, now you can write this rational function r of x as equal to the quotient, which is 2x plus 1, plus the remainder, which is 6, divided by what you had, x squared plus x minus 1. Right? This is the
Yeah,
division statement.
correct.
Perfect. So that is how. What does it mean? When x approaches infinitely large value, right? It could be positive, or when it is approaching negative, sorry, it could be positive or it could be negative infinity. In that case, what happens? Your function, rational function, is actually approaching 2x plus 1, right?
Correct.
Because this value approaches 0, correct?
Yeah, correct.
But remember, this is some positive value, correct? This is a positive value, correct?
Yeah, correct.
So that means if you are approaching, as x approaches infinitely large value, the function will approach from above because something remains. You get the idea?
Yeah,
So we also get
correct.
this behavior near the asymptote. And this line which I have drawn will be the line of oblique asymptote 2x plus 1 on the graph. You get the idea?
Yeah, I get the
And
idea.
the function will approach from top. Perfect?
Yep.
So that is how it is going to be. And in this particular case, if x is very large, infinitely value, but negative, in that case, will it approach, when x is approaching negative infinity, will it approach from top or bottom? How will you say that?
Uh, would you No, I'm not sure either.
Okay, so have a look at this denominator. It is a quadratic function with leading coefficient of positive, right? What?
Yeah,
So
correct.
that means this denominator, the parabola, will be actually like this, right? Will be always positive at x infinitely large value, right?
Yeah, correct.
So clearly it is going to be positive. So even at when x is approaching negative infinity, this value is going to be positive, and therefore there also it is going to approach from the top. You see that
Okay, I see
in this
that.
particular case. If this would have been cubic or a linear, it would have approached from below, right? Because that
Yeah,
will become negative for negative infinitely large value. Perfect?
yeah, perfect.
So you clearly understand that we do have oblique asymptote whenever the numerator is divided by a denominator whose degree is of difference 1, numerator being higher. So I just made a statement which is whenever the degree of numerator is 1 higher than that of denominator, we will get an oblique asymptote. Is my statement always true, sometimes true, or never true?
Is it sometimes true?
Perfect. How can you say that?
When there's a common factor. Uh,
Okay, so let's look into this.
okay.
So we have a rational function, let's say f of x, and we have some numerator and some denominator. And we know the degree of numerator is 1 higher. So in that case, we are saying oblique asymptote is there. However, if we have an example, as you said just now, if I have x squared minus 1 divided by x plus 1, correct?
Yeah, correct.
Now here, clearly, the degree of numerator is 1 higher, right?
Yeah.
Do we have an oblique asymptote?
Uh, no,
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 correct?
correct.
That is very true. As normally, it is assumed that we'll always have oblique asymptote whenever degree of numerator is 1 higher. The statement is we can have, right? So do we have? So oblique asymptote. So we can have. Do you understand the word can? We may not have sometimes, because in this case, what really happens, as you rightly said, I could factor the numerator as x plus 1 and x minus 1. And when I divide by x plus 1, in that case, these cancel. So we have a whole at x equals to minus 1 here,
Yeah,
right?
that's
But
correct.
we could write this function as equal to x minus 1 with a x value not equal to minus 1, okay?
Yeah, correct.
And if I draw this function, how will it look like? It is x minus 1. That means a straight line going kind of with a slope of 1, gradient of 1, y-intercept of minus 1, correct?
Yeah,
However,
correct.
at minus 1, it is not valid. So at minus 1, I will have a hole. Do you see that part?
Yeah, I see that.
And the value at minus 1 is going to be, when I substitute, minus 2, correct?
Correct.
So that is how you could prove or say that oblique asymptote can be there if degree of numerator is 1 higher than the degree of denominator. But it is not always true. This could be an excellent example to show the same, correct?
Yeah, correct.
Right. So here you also see there were those factors which cancel away. They lead to both. And in this particular example, we do not have any vertical asymptote, right?
Yeah, correct.
Now my question to you is, will all rational functions have a discontinuity? But we have a discontinuity, which is pole at 0. So now my question is, will all rational functions have discontinuity?
Uh, no. If the
Yes.
if the numerator is the denominator is like x squared plus 1, it'd always be positive, right?
Correct. Great answer. Great answer. So will rational function have discontinuity? right? So not always, right? So the answer
Yeah.
is not always, correct?
Correct.
These questions are very interesting. Sometimes true, always true, these type of questions, right? So for example, I could give a function like x squared plus, let's say 2x minus 1 divided by x squared plus 1. Now in this case, my denominator is continuous. Do you see that?
Yeah, I
There
see that.
is no x-intercept for x squared plus 1, right?
Yeah, correct.
This is never 0. In fact, it is always greater than equal to 1, correct?
Yeah,
So
correct.
in this particular case, our domain is all real numbers. That is what we are getting into, right? Domain is x belongs to real numbers for this rational function. You get the idea.
Yeah, I get the idea.
So when we are talking about rational functions, let us be very clear that rational functions may or may not have discontinuities.
Okay.
Rational functions could be continuous, right?
Yeah, correct.
That's very important. Even if I take up another example, just to give you a very simple example, let us say we have a rational function which is 1 over x squared plus 1. Can you graph this function? This is also a reciprocal function, right?
Yeah, correct.
Tell me, how will you graph this function and how will the graph of this function look like?
Uh, you could graph by uh, you could find the vertical asymptotes first, or
There are
there won't
no,
be any.
no, there are
There
no
won't be any.
vertical
Right.
asymptotes, right?
Yeah.
So graph reciprocal function, I'm writing, right? And this function domain is all real numbers, right?
Yeah, correct.
Where the domain belongs to real numbers, right?
Yeah.
X belongs to real number, I should have written whatever. See the beauty. So we'll follow the general procedure of graphing a reciprocal function, right?
Okay.
So let us say that function f of x is x squared plus 1, right? And therefore, we can say that g of x is reciprocal of f of x, correct?
Yeah,
So
correct.
the idea is first graph f of x. So f of x is a simple graph x squared, which is shift 1 unit up, right?
Yeah, correct.
This becomes absolute minimum for f of x. So we've drawn f of x. Now reciprocal really means that 1 over that value, right?
Yeah,
So what is 1 over 1? 1 over
just one.
1,
Yeah.
just 1, right? And when this value is approaching infinitely large, what happens to the reciprocal value?
It's also it's approaching 0.
And since it is positive, it will approach from the above, right?
Yeah.
And on this side also, it is approaching 0, correct?
Yeah, correct.
And from the symmetry, you can say the graph will be kind of like this. Do you see the graph?
Yeah, I see it.
So that is kind of a graph, bell-shaped graph, which you will get. And of course, you have horizontal asymptotes y equals to 0 in this case. And this particular point, which we came across here, is called invariant point. Let me write down.
Okay.
Invariant, it is common in both. It did not change, right?
Yeah.
So in the graph of reciprocal function, which we've just taken, we have invariant point 1 because it was just same for both the values. Clear?
Yeah, that's great.
Perfect. So since we are at reciprocal function, let me also take with you some examples where we'll understand basic procedure of graphing reciprocal function. So what I will do here is graph a function first, right? So I'm graphing a function first. Let us say it's a parabola. Okay. Now we need to graph the reciprocal of this function, which is 1 over f of x, correct?
Yeah, correct.
Tell me, how will you sketch a graph of a reciprocal function when the graph of the function is given to you?
Um, if the graph is given, uh, You could try finding some points on the graph.
And the best points are the x-intercepts.
Yeah.
So the x-intercept for a reciprocal function, the x-intercepts of the function will lead to discontinuities, right?
Yeah, correct.
So let us say, let's just give them some values. Right? Let's say this is some value a. Let's write a and b. Doesn't matter. In
Okay.
that case, we have 1/0, which is a vertical asymptote, right?
Yeah.
So straight away, at every x-intercept, draw a vertical asymptote. I purposely made a hole there, saying that there is a discontinuity, right? So we say
Yeah,
x
correct.
is not equal to a and b. Does that make sense, right? General?
Yeah.
Now, second, the portion which is negative, we know graph of negative will be negative, right?
Yeah.
So
Correct.
we know a few key points. Let's understand. We are talking about f of x 0, right? Change to g of x vertical asymptote. Make sense?
Yeah, makes sense.
F of x, if it is greater than 0, in that case, g of x will also be greater than 0. Positive, positive, right?
Yeah.
If f of x is less than 0, then g of x will be negative, right?
Yeah.
If f of x is approaching infinity, then g of x will approach 0, right?
Yeah.
If
Correct.
f of x is approaching 0, g of x will approach infinitely large value, reciprocal. You get the idea.
Yeah. I get the
And
idea.
if f of x is equal to 1, then that is same as g of x. You get the idea.
Yeah. Correct.
And that is our invariant point. Is that clear to you?
Yeah, that's clear.
So, my simple steps to sketch a reciprocal function is identify the zeros of the function, draw vertical asymptote, write them as your restrictions. Clear?
Yeah, that's clear.
Now think about 1 and minus 1. Let's say this is minus 1. Is it okay?
Yeah.
So wherever we have 1 and minus 1, those are my invariant points. Do you see that?
Yeah, I see that.
Because the reciprocal is going to be same for 1 and minus 1, right?
Yeah,
The
correct.
rest of the portion is like 1 over x. You get the idea.
Yeah.
So I'm going to sketch on the first, the right hand side, when it is infinite. Do you see this?
Yeah,
Because here
I
it is
see.
approaching 0, the function, and that is my horizontal asymptote. Do you see that?
Yeah, correct.
So I do have a horizontal asymptote, which is right there. Since the degree of denominator was 2 higher than 1, right? 0 in the degree
Yeah,
of
correct.
denominator. Now let's look into the center portion, which is negative. So reciprocal will be negative. And let us assign some value c here for the maximum value, right? It
Okay.
necessarily it will not be in the center, right? Let it be here. Let it be here, okay? I'll just
Okay.
shift it to right a bit. So that is the maximum, the minimum value for the function. So the reciprocal will give that as a maximum value, right? 1 over c.
Yep, correct.
And we have -1, -1. So the graph will be kind of like, do you see this graph?
Yeah, I see that.
Where this point will be 1 over c.
Okay.
So that becomes a local maximum. So the minimum becomes the maximum, right?
Yeah.
When you do that. And
Correct.
maximum will definitely become the minimum when you do the reverse. Do you
Yep.
see the graph of a reciprocal function? You get the
Yeah.
idea,
Yeah, I
correct?
get the idea.
Is this absolutely clear to you?
Yeah, it's clear.
Perfect. So in general, we are going to have this kind of a graph. Okay, just to test you out, let me give you another graph and ask you, how will you make a graph for reciprocal function? Okay,
Okay.
so there you go. I have a graph here. Right. Let's say this value here is 2 minus 4. Now tell me, how will you proceed to draw? This is f of x.
Yeah. Uh, So there would be a vertical asymptote at -2.
Very good. Correct.
And you could try and at y equals 1, it would be a point on the graph. So it would be
Invariant point, yes.
yeah,
On the reciprocal, yes. How will the graph look like?
and so the two curves on the top would approach the -2.
Right? So we know y equals to 0 is
Yeah,
your horizontal asymptote.
yeah,
So you will
correct.
go through like this, right? Correct?
Yeah, correct.
Going through -1. Do you see that?
Yeah,
So
I see that.
this is kind of 1 over x. Since the graph was positive, non-negative, right? Do you see? Our reciprocal is also non-negative, right?
Yeah, I see that.
Right. Now, one of the very common question here is, can you find the interval of increasing and decreasing for the reciprocal function?
Okay.
Yeah, tell me.
For the reciprocal, it would be that it would be -infinity to -2,
Very good.
and then for the decreasing, it would be -2 to infinity.
Very. So we have increasing and decreasing interval. This is increasing and this is decreasing. Perfect. And
Yeah.
where is the function g of x positive greater than 0?
It's positive. Um. Well, it's always positive.
No, minus infinity
Oh,
to minus
two.
2 and from
Right.
minus 2 to infinity. So
Oh
don't
yeah.
make that mistake, right? Because
Okay.
you are very close to 100%. Don't lose this 0.1 mark. Perfect.
Okay.
So that is absolutely correct. So that is how we are going to sketch a rational, I should say, the reciprocal function in this particular case when given the graph, right? So
Yeah.
are all these concepts absolutely clear to you?
Yeah. It's clear.
Perfect. So, do you have any questions?
No, I don't have any questions.
Okay, great. So we'll end our class here, and
Okay.
I'd like you to summarize today's learnings.
Okay.
So, Krishna, can you please summarize today's learnings?
All right. So we learned how to graph a reciprocal function, how to find the horizontal and vertical asymptotes, and we also learned about oblique asymptotes.
Yes.
Yeah.
Great. So with that, we are going to end our class.
Okay.
Thank you and have a great day.
All right. Thank you.